Hi everyone, welcome to the theory seminar. We are excited to have Dr. Vincent Cohen-Addad today as our speaker. Vincent is a research scientist at Google Research Zurich. Prior to joining Google, Vincent was a CNRS researcher at the Sorbonne University, and before that, he was a recipient of a Marie Curie Fellowship at the University of Copenhagen. His doctoral thesis, done at ENS, has been awarded the EATCS Distinguished Dissertation Award. In the recent years, Vincent has made many significant contributions to the design of algorithms for clustering problems as well as network design problems, with an emphasis on problems arising in the context of data analysis and machine learning. So, we are very happy that Vincent has agreed to give us a two-part talk. So, today he's going to talk about the algorithmic advances on metric clustering, and in the next part, which is on 18th of October. Please note that this is a Monday. He's going to talk about the algorithmic advances on graph clustering. So thanks everyone for joining us, and Vincent, over to you.
Thank you very much. Thank you, and welcome everyone for this talk. Thanks a lot to everyone for the nice invitation to give a talk today. So I would like to keep the talk like pretty interactive. So if you have questions, like feel free to stop me if it's going too fast, or if it's like if there is something unclear, you should really please stop me and we can take more time. Okay, so this series of talks is in two parts. The first part is on metric clustering, which is some topic that is very popular in machine learning, and the other one is like graph clustering, which is like maybe now starts to be more and more popular in machine learning, and it was maybe more popular for combinatorial optimization people before. So okay. So this talk today is based on a series of work with a lot of people, a lot of co-authors like Wei-Yong Lee, Kartik, Phil Klein, Claire Mathieu, Marcin and Michał Pilipczuk, David Solpik, my student, and Andreas Feldman. And thanks a lot. And it's if you have also questions, feel free to dig up into these works as well. Okay. So what are we gonna look at today? We're gonna look at metric clustering. So in metric clustering, our goal is to partition points that are lying in a metric space based on the distances between the points, meaning that we would like to find a partition of the points such that points that are close to each other are in the same part. Okay, and these are like two different applications domain that are well modeled by this formulation, but that are kind of different. One of them can be sort of as like, if you have geographic distances. So if you are trying to maybe partition, like here it's Texas, onto regions. No, it's not Texas. I don't know what it is. It's like some region of the US. Maybe it is Texas. Into regions. Into districts on the left. So here you have Texas. You want to group Texas into regions that are very well connected. And here there you are dealing with geographic distances, and this could be useful if you want to divide, for example, a region into subregions that have some specific properties that are tightly connected. And this is something we use, for example, for computing redistricting. Or like for facility location. And then there is another type of problem that we like to solve is like we have a bunch of data elements, and we can set up distances between the elements so as to represent similarities. So for example, we can say, okay, we have ducks, and ducks are close to each other. So now we have small distances between the different ducks. And we have maybe large distances between animals with long ears, and these are two animals with long ears. And then if we have this as a notion of distance, then we would like to have short things that have like short distance, like animal with long ears are close, and ducks, they should be in the same clusters, and they are possibly at larger distance. So that's the overall thing when we have like data elements. And that's also very useful if you were trying to do unsupervised learning or different data analysis tool where you have to define first your distance between the elements. You can do it by finding good embeddings of the images, like the starburst embeddings, different type of embeddings that map images onto Euclidean space, and then you can look at the L2 distance, or like the Euclidean distance essentially, between the images, between the embeddings of the images, for example, and you get some sort of notion of similarity or dissimilarity. And you can do the same thing with like videos, with like different things. As soon as you have an embedding that embeds at the same location things that are similar, embed at different locations things that are like dissimilar, then you are able to use distances to represent similarity. Okay. So these are like very high level goals, and maybe the question you can ask is like, how can we make them a little more formal if we want to design algorithm and prove things about the algorithm? And one way you can do it is by the following objective, which is you can look at define a metric space that is given by your points, like the Euclidean space. You have like a set of points gamma here. And then a distance between the points, between pairs of points. So our input for the problem is what we call a client set, but it's just a set of points of gamma in the metric space, so a set of points in the metric space. And together with a set of candidate centers. So these are points of the metric space that you can pick from, and you will pick from this set to find good representatives of your input client set. So what you want to find is partition of the client set. But in order to do so, you are allowed to pick like representative sets, representative points from the candidate center set. And then you have a parameter k, which is the number of clusters you want. And your output, which now will clarify a bit more what the input was, is find a set of k representatives. So that's the number of clusters you want. K representatives C that we'll call centers from the candidate center set. It has to be a subset of the candidate center set. And you want to minimize the sum of the costs from each point to the mean cost center. And the cost could be like the distance, could be the distance squared. You can have different flavor of it. But essentially, what you want to find is like in other words, you have a client set X that are points. You have some set of possible representatives. You want to select the k best representatives from your representative sets, and then look at the and minimize best in the sense of minimizing the distance to the closest representative. So from there you can define the k median, where you minimize the sum of the distances, the k means, where you minimize the sum of the distances squared. And these things, these two problems are like very old and famous problems, so it's interesting to look at them.
One question.
Yeah.
So, what other problems are now, like K center, for example? What is the notion?
Yes, exactly. So the K center, then it's like going to infinity, like letting this power go to infinity, in the sense that you will minimize the sum of the, you will minimize the maximum distance to the, you want to minimize the maximum distance to the closest center.
So general LP norms are studied in this case, like one is one.
Yeah. So essentially, I think the most famous one are like k-means. The most famous one is k-means. K-median has been known as well, also for historical reasons. But essentially, any LP norm can kind of make sense in the sense that, this is how much you care about outliers or not. Like essentially, in the K center, you want to minimize the maximum distance. So you can really, there is no outlier essentially. If you have one outlier, then it's gonna make your cost very, very bad. Now in the k-median, the fact that you have outlier doesn't change much the location of the median. So it's a little bit the trade-off between how much you care or not about outliers in some sense. And there's also a computational issue maybe that, in Euclidean space, if you want to find the one point that minimizes the sum of the distances to the mean, like computing the mean, for example, is very easy in Euclidean space. You can just average the points, the vectors of the points of your cluster. Now, if you are looking at the median, it's slightly more tricky. If you are looking at the piece power of this, then it's slightly more computationally expensive. But it makes sense to look at them, I think. And we had like a NeurIPS paper this year where we actually show how you can do it, like for example, for like different piece power and why it's how to do it. So yeah, I think people are interested as well in that thing.
Thanks.
Hi, Vincent.
Yeah.
Would you be able to consider spaces which are not just like the metric space, like constraints?
So if it's not a metric space, then the problem becomes really hard. So good. So let me not answer this question now, and let me answer it like later, and I will. It's gonna be clear what's gonna happen. But essentially, the problem becomes way much harder computationally if you don't have a metric space. It's possible to do it, but then it's essentially you are trying to solve like the set cover problem, which is like, you can't get like a better than log n approximation. It's a hard computational problem then. But I'll come back to it later. Yeah, that's a good question. Okay, so what's also useful is to consider like a soft constraint version, like it's you can say it as a Lagrangian relaxation of the problem, where it's exactly the same thing, but instead of having like a parameter k on the number of centers you want to cluster you want to have or center you want to get, you have an opening cost, which assign like some sort of cost for each possible candidate center. And then instead of like picking k representative, you can pick any number of representative. It doesn't have to be k anymore. But then what you want to minimize is the sum of the opening cost, like of this cost of the elements that you select. Actually, this should be a C here. I'm thinking right now. So all the sum over the elements in the set that you have picked of their cost plus the sum of the minimum distances. So then you kind of. Now you don't have this hard constraint on k, on the number of clusters you're going to get, but then you have to trade off now you get the trade-off between the quality of the solution you get in terms of distortion here, dispersion of the points versus the centers, and in terms of like, how many points and what you're going to pick, centers. Okay. Good. So let me try to get through a journey to center-based. This is center-based because we are picking representatives, so it's called center-based metric clustering. And this is like we're going to try to define this map a little bit here, where we have like different region of the map, where depending on the metric that is underlying your points, you can get different results. So for example, if your metric is completely arbitrary, this is like a dangerous region because like the input that you get, they don't have that much structure. Just general metric is just distances satisfy triangle inequality. So you just have a triangle inequality. So now what can you say when you only have triangle inequality? It's a good question. Then you can look at, okay, then you can move away from just triangle inequality to high dimensional. Like even if I give you n points in n dimension, they still lie in some Euclidean spaces. So there is still some properties on the metric space. You can't, general metric are such that you can't represent all of them by high dimensional Euclidean space. So in that sense, they are more general than high dimensional Euclidean space. They are high dimensional, they are general metrics that you can't realize here. So maybe something that is slightly easier from the general metric is like high dimensional region. Like something where, of course, it's Euclidean, so there is much more structure that you can use, but it's still high dimensional, so it's not that easy. Okay. And then you can look at you can go and make your life easier and easier. You can say like doubling dimension, which is like a discretization that is just like generalization of Euclidean spaces. It's not too important to go too much into the detail, but it's like, sometimes you have metric spaces that are not quite Euclidean in the sense you don't have an embedding of the points into RD, but you still have low dimension, like if you think of a grid, for example, grid is not a Euclidean set because you don't have necessarily an embedding of the points onto the plane, because maybe it's giving it to you as a graph, but it could still have bounded doubling dimension. So for example, this is like, slightly easier because like, grid is like simpler. And then you have the low dimensional cases. There is the plane or like graphs that are planar, for example. These are like metrics that are slightly easier. Okay, so we can try to understand clustering in terms of this. And to understand
question here.
Yeah.
So when you say that any general metric space cannot be embedded into a high dimensional space,
Yeah.
Euclidean space, you mean with a
Sorry.
like exponential block? For example, there is this Borgian theorem which says that you can embed this in with a log n distance.
Yeah, exactly. So I'm saying like isometric embedding, like when you don't distort the distances by too much. Yeah. Otherwise, it's true that if you accept that the distances can be distorted by a factor of log n, then indeed like Borgian embedding is gonna come into play. You can ask like what is the worst distortion you can get, but if you want to preserve the distances exactly or up to 1 plus epsilon factor for like arbitrary small epsilon, but even arbitrary small but constant epsilon, then there are always I can always come up with a general metric that you won't be able to embed.
Thanks.
Sure. Okay, so to understand a little more like the flavor of this, I want to take a set cover perspective on clustering. So a set cover instance is just very combinatorial problem where you have a set of universe elements and a collection of sets, S. And what you want to know is whether you can pick K sets in S, such that you cover the whole universe. All right, so you have this collection of sets. You want to pick at most K of them. The union of these K sets should be containing the whole universe. So it's a very basic combinatorial problem that people in computational complexity, approximation algorithm have looked at for decades, and it's a hard problem. So what we don't know much about, like we know a lot about it, but we don't know better than like a log n approximation. It's NP hard to get better than log n approximation, in fact, and it's not so easy how we can. It's not a very easy to deal with problem, and in fact, I want to argue that clustering can be seen as a metric version of this problem because there is no metric space right now. It's just like combinatorial. But we can try to model it using K-median. So how can we create a K-median instance that will model the set cover instance? Well, take your set cover instance, and then for each element of the universe U, you can create a client point that you would like to cluster. And for each set in your collection here, you can create a candidate center. Okay. Now, let me create a metric space, or let me create distances or dissimilarities between these points. I can say between a client and a candidate center, I'm going to set the distance to be 1 if the element belongs to the set. Okay. So I have one client for each element of the universe, one set, put distance 1 if the element is contained in the set. And then let me put a distance that is very large otherwise. If the element is not contained in the set, I put distance like infinite. Okay. So this is not a metric space, right? Because I'm not sure the triangle inequality is satisfied and so on. But let me put infinite for now. And now I can decide whether there is a solution to my set cover instance by just looking at solving the K-median problem, because I can say, okay, if I can find K candidate center among my candidate center set, I can pick K centers there. So that means I pick the K corresponding sets, and everyone will be paying exactly 1 if everyone is covered, or maybe not. Maybe one guy will be paying infinity because it's not covered, so it has distance infinity to the rest. And so I can decide whether there is a K-median solution of cost U, the size of U, the size of the universe, which is like everyone is paying 1, or there is no such solution for K-median, meaning that it's at least infinity, because that's the other distance in the graph. And then that means that one element is not covered. So this is a complete characterization of K-median. So that's why I'm saying, like, if you don't have metrics, if you don't assume that the K-median input is in the metric space, then I can put this distance to be infinite, for example, and I can model the set cover instance this way. And so then it's not as it's like, you know, you can't do anything essentially. Like, you know, here you can't find any approximation algorithm for this problem, right? Because it's like deciding between 1 and infinity. So if you have a 3 approximation, you can still decide between 1 and infinity. So it's not possible to approximate this problem. So it's a hard problem from that side. Okay. But here I was cheating a lot because I was putting distance 1 or distance infinity. 1 if it's in the set, infinity if it's not in the set. And of course, the question you can ask is like, you know, if I'm a metric space, how large can this very large be? Can I really put infinity? It's not clear because it has to satisfy triangle inequality. Okay, so I'll come back to this. So let's make this slightly more formal. And we need to look at the max coverage problem. So the input to the max coverage problem that's going to be very useful for this talk is again a universe, a set of universe elements, and a collection of subsets and a parameter k. And the goal is to find k subsets in S, k sets in S, that you cover a maximum fraction of the element in U. And there's the theorem by Feiger that says that you know, it's hard to distinguish between an instance where you can cover everything and an instance where you can cover at most 1 minus 1 over e plus epsilon fraction. So it's, you know, it's not possible to design an algorithm that can distinguish between these two things. So maybe you can find a
Vincent, question.
Yeah.
What is the distance between the sets themselves? Like in the previous slide, you mentioned that.
Yeah, exactly. So I didn't specify it. Let me, yeah, exactly. That's the thing. Like now I didn't really. So one thing you can do is like look at you just put the edges of length 1 between the client and the set. And now you can look at the shortest path distances, for example, in this graph where you have distances. And that's the way you could set, for example, the distances. And of course, then that would be a metric space, but then I'm not putting infinity anymore. So I'm going to come back to this very, very soon. And I'm going to come back to it just using this max coverage because it's going to make the things slightly more easier to analyze. So yeah, so I'm just coming back to that in like one slide. So yeah, so this problem is essentially set cover problem, but instead of like you want to cover everything, you just want to cover a maximum fraction of the universe element. And so it's hard to distinguish between these two problems. So now let me take a max coverage input, okay? And so set of universe elements, set of sets, and parameter k. And from there, I'm gonna create a metric k median instance. So again, this is my set of universe, my universe points, my universe of the k coverage, like max coverage instance. And it's also my set of clients, like, you know, for each element of the universe, I'm creating a client, so a point that I want to cluster. And then on the other side, I'm going to create candidate centers for the sets of my max coverage instance. And then again, I'm going to put distance 1 if U1, this element here, the corresponding client is at distance 1 of set S, of the candidate center of set S, if U1 is in S. And otherwise, I'm going to put distance 3. And then I'm going to say that, okay, max coverage is value 1. You can solve everything if there exists k candidate centers such that everyone is at distance 1 from one of the candidate centers in my k candidate center that I've chosen. So the optimal k median cost then is the size of the universe, U. And in the no case, so the max coverage is at most 1 minus 1 over A. Then for any set of k sets that I could pick here, no matter which k tuple I pick here in my candidate centers, at most the 1 minus 1 over A fraction of the clients are at distance 1. But there are some clients like this one that are at distance 3 from my things. And the rest, so is at distance 3. So the total cost for the optimum solution for k median is of cost at least 1 times 1 minus 1 over e fraction of of u plus 3 times 1 over a fraction of u, which is like 1 plus 2 over u. Okay, so that's the best you can hope.
But this is still not a metric, right? After putting distances as 3.
Sorry?
It's still not a metric, right? After we put this distance.
So let me argue that now this is a metric space. Okay, let me argue that this is a metric space because okay, why is it a metric space? Because so here this distance is 1, and now this distance is 3, and so the way it could not be a metric space if there is a shorter path than 3 here. But the only way I could have a shorter path than 3 here is if I go to some set that covers it, which is at distance 1. Then from there, I need to go back to a point that is in both this set and that set. And if maybe this point here is both in that set and in this set, so then from here I could pay 1, then 1, then 1. So that's 3, and there is no really shortest path from there. I can't make it smaller than 3. I mean, essentially I can put the distance between all the sets to be 2. Okay, all the sets here I can make the pairwise distances to be 2. All the elements I can make the pairwise distances to be 2, and this will not be violated. So then now if I want to go here, the only thing I can do is like 2 and then 1. Or I can do 1 and then 2, but there is no shorter than 3. And if I set distances to be 2 between any set here, I can't. There is no shorter path than 2 here, right? Because maybe you have one element that is contained in both sets, in which case it's going to be 1 and 1, and then the distance is 2. But you know, I can't make something smaller than that. And same thing for the elements. Maybe these two elements are in the same. Maybe these two are in the same set here, so the distance can be 1 plus 1, so it's 2. But there is nothing shorter than that.
And can we trade off this 3 for the distances between the sets?
You mean like can I increase it and then like make the distances in the set higher?
Yes.
No, I mean like the issue is that maybe between these two sets, there is maybe between any pair of sets here, there is always one element that is contained in both sets. So maybe there are 2 sets here such that you have distance 1 and 1, because this guy is maybe this guy is included in both these sets. So then I can't make, if I want to satisfy triangle inequality, I can make it only 2. There is no chance I can make it smaller because larger. If I make it 3, then there is a shortest path 1 plus 1. So that's not good. So so it's not. So the only way you could do it is that if you had pairs of sets for which there is no that are disjoint. Okay, there is a non-intersection between the pair of sets. Then you can increase the distance a little bit. But now I'm not assuming anything on the input of the set cover instance. So maybe all the sets are overlapping. This I don't know. So then in that case, I can't do much. I have to put a 3 there, and then it's like then that's the bound I'm getting. And so from there, I can directly derive the theorem that says that it's hard to distinguish a Chemidian instance where everyone is paying 1, or like distances is of all the elements in X is X, versus an instance where the distances for all the elements in X, the sum of the distances, is at least the optimum solution has cost at least 1 plus 2 over e minus epsilon times the size of X. So that's the first hardness result that we can derive from there. It's not from me, it's from Guo and Kuller in the late 90s, but that's essentially like the result you can get. And here is really like the thing that this point is that if a universe element belongs to a set, the distance is between the 2 corresponding elements is 1, so I can't really make it like much smaller than much larger than 3. It has to be 3 that's kind of tight. And here, sorry,
is this result tight, or like what is the best known gap present gap for this problem?
Okay, good. So the best known gap right now for metric median is like 2.6. And I'm going to come back to it later, but yeah, so we had it's like 2.6, and the question is like, can you go down to 1 plus 2 over E? And one result that we had 2 years ago at IISc was showing that if your running time can be 2 to the k poly n, so it's like fixed parameter tractable in k, then you can actually achieve the 1 plus 2 over E, and that's also tight in terms of fixed parameter tractability. So you can solve it optimally. You can solve the problem optimally if your running time is n to the k, because then n to the k, you can try all possible sets, like all possible candidate centers. That's n to the k, so like in n, maybe n to the k plus 1, you can compute the solution, optimum solution. But if you want something that will run in time 2 to the k poly n, then the same lower bounds apply, but we can show a positive algorithm, like an upper bound that will be 1 plus 2 over E. So in the FPT world, 1 plus 2 over E is tight. In the fully polynomial time, when you have something that is poly k, poly n, then the gap is still like 1 plus 2 over E on the lower bound side and 2.6 on the upper bound side.
Thanks.
Sure. Okay. And now there is another question you can ask, is that, okay, here we were only constrained by the triangle inequality. And the challenge was to say, okay, what is the best we can do in terms of hardness, given this triangle inequality going on? And now you can ask the following question, which is that if you have other additional structure on the metric, like for example, if you have to try to do the exact same reduction, but the points have to be in Euclidean space, for example. If it's like high-dimensional Euclidean space, or if it's low-dimensional Euclidean space, or if it's like the distance is given by like some kind of Jacob distance, or if the elements that you have are like strings, then it's gonna be like edit distance. Maybe you want to look at edit distance, or if it's like a planar graph, for example, then you can have like or a grid or something. Then how does the then it's not clear that I can put the 3 anymore, because it's not clear that I can embed such a structure in low-dimensional or like low-dimensional or other metric spaces. So yeah, so that's the question I'm asking right now. Like, how is this hardness evolving if you have different metric spaces there? And yeah, what we're gonna try to go over in the next the rest of the time right now is through the planar case, low-dimensional, like essentially low-dimensional Euclidean spaces, and also what if it's like high-dimensional Euclidean space, like low and high-dimensional, essentially low and high-dimensional Euclidean space. Okay, so for example, for k-median, we know that when we are working in the plane or in low-dimensional Euclidean space, there is some results who get us like something that is like this is like quasi-polynomial running time if your d is greater than 2, and then this was improved later to like fully polynomial time. Like you have an exponential dependency on d. In fact, it's a doubly exponential dependency on d. Then people knew about this result for like more than 20 years. And the question that one could ask is like, okay, this is only for k-median that was known, and what if we try to extend these results to maybe more general metric than just Euclidean? So for example, something that we can look at is doubling metrics, which essentially says that it could be a discrete metric, but the doubling metric is essentially like if you have a ball of radius 1, you only need a constant number of balls of radius 1/2 to cover the ball of radius 1. Okay, so it's something that is quite almost like Euclidean space, but not quite. Like there is no embedding. It can be given by a graph. Essentially, a grid is such a thing. Like if in the grid, if you have a ball of radius 1, then maybe you need like only a constant number of balls of radius 1/2 to cover the vertices. So you can ask, is this 1 plus epsilon? And this is 1 plus epsilon is definitely bypassing the hardness bound of 1 plus 2 over E. And the reason it's bypassing is that this reduction that I presented, you can't embed it in the plane, for example. If you want to embed the hard set cover instances onto the plane, for example, you will run into trouble. You won't be able to find an actual embedding of the points and of the candidate centers that would realize these distances, even up to a pretty good approximation factor. Okay, so you will have to have big distortion on these distances if you want to do that. Okay, so let me go back. So let me explain how people were solving this question like 20 years ago. Essentially, people were dividing the tree into using a random recursive decomposition where you would recursively divide the plane into regions, and then you will place some portals on the boundary of the regions, such that if a client has to connect to a center or facility in the facility location case, you can do it, but it can't connect directly. It has to go through the portals. So essentially, the portals are like some sort of filtering or like some pre-clustering points that are on this region. If they want to join the clusters centers on the right region, they have to go but through the portals. And this is very nice and very nice structure, because then you can do a dynamic program where the table entry is just given by the distance from each portal of the region. So for example, for region R, you can look at, you only care about what is the closest center outside to that portal. Because now if I have a point in region R that wants to connect to the outside, then I know that it has to connect by one of my portals. And so I just need to remember who is the closest portal to each of my portals. And since the number of portals, I'm trying to bound the number of portals essentially. Like if I have P portals on the boundary, then the running time is going to be 2 to the P, and then I can do something else, because the number of options that I have on the boundary for the distances to the closest portal outside is essentially like constant, or like it's not too big. You can make sure it's not too big. So the question is like, if I have one portal, this is very nice because this is, pretty good running time. If I need like 1,000 portals, then this is like 2 to the 1,000, it's too much. And so the question you can ask is like, how should P be? How large it should be, such that, because there is a trade-off here, right? Because I'm saying like, in that case, the client that was connecting like this originally, directly with a direct path, has now to go through the portal. And so now the blue path that you see now is longer than the original black path. So if I'm making this, if I'm forcing the solution to follow this weird path here to connect, then I'm incurring some error. And so I'm going to make maybe some mistakes in the dynamic program, because I may be finding a solution that is more expensive than the actual one, the actual original opt one. So here is what people were doing before. If you have a facility and a client that are split by a line of length L, so in the sense that here, the length of this line here is of length L, between that is splitting these 2 points, then if I place P portals on this line of length L, my detour is going to be, if I put the portals like at equal distances, it's going to be L over P. And what we can show is that with this random partitioning, you can show that C and F are separated by a line of length M with a probability that is distance between the two divided by L. Like this is the probability you get. So now the expected detour that I'm going to make by forcing C and F to connect through a portal is going to be the probability that, by a line of length L, is the probability that they are cut by a line of length L times the detour I'm going to pay, which is L over P. And so in expectation, the detour I'm going to make for a line of by line of length L is the distance between the two divided by P. So now the number of different lengths I can have on my lines is essentially log n, because I'm going to have like, I'm going to making like a decomposition that has depth log n. So the total detour that I'm expecting to see here is the sum over this over the all possible lines lengths, and so it's like log n divided by p times my distance. So if I want that the distortion, the detour, the total detour I'm going to see by because of the portal, if I want this to be bounded, like let's say an epsilon fraction of the whole distance, then I need to use p portals where p has to be like log n divided by epsilon. And actually, this was only done for the case of the plane, so actually it has to be to the d. So the running time in that case would be exponential in log n over epsilon to the d. So if I just want to use tree embedding, doing this, like a tree decomposition, essentially, tree decomposition of my metric space, and place portals so that points can connect, I need a lot of portals. I need at each step to use like log n over epsilon portals. So yeah, there were two problems with this approach. So if we have like log n portals, then it's not very good for doubling metrics or like getting like good approximation algorithm, because we don't know how to simplify this approach for even simpler problem than k-means and k-median. Like even if you were to do like, you know, maybe a traveling salesman problem, which has received a lot of attention as well in this kind of context, it's not clear how you will get something smaller than log n portal. So log n portal is not very good. And especially the interesting thing is here is that the thing, and that's why people didn't know. So the thing here that I want to stress is that people only knew about to say k-median. So this nice, cute analysis that I give you right now, how to show that, you know, if you do portals and stuff, you can get a solution for k-median, only works for k-median. And so for like 20 years, people had no clue how to make it work for k-means. So we know since 1998, even something quasi-polynomial time for k-median, but we don't know anything for k-means. Like, you know, maybe k-means is as hard as like general metric case. We don't know. So and the reason for this is that the analysis can't work for k-means, because if I have an instance like this where the black points are the clients and the green points are the optimum centers, then no matter where I split, the detour I'm going to make is like really big, because in the k-means problem, I'm going to have to square the distance. So now the detour that I'm paying is squared. So if I want to look at the expected bound that I was showing on like 2 slides ago, now I still get that the probability of being separated by a line of length L is still the distance between C and F divided by L. But now the distance that I'm paying, the detour I'm paying, is like L squared divided by P squared. So now this doesn't end up being like dist over P as we were happy with before. Now it's like L times dist over P squared. And L can be very large at some points. Like at the very beginning, this is very large. So now if I pick, no matter how I pick a vertical line here, I'm gonna maybe split, you know, one optimum cluster into 2 regions. And then there is no chance I can use directly the dynamic program and the detour to bound this, because it's gonna be paying an epsilon fraction of n squared. And the total cost here is n. So that's not good at all.
One question.
Yeah.
So these portals that you created are, they look like some uniform points along these grids or something like that, but
yeah,
it's instance independent. But depending on your instance, can you create some kind of special portal such that you don't incur so much loss? Or
yeah, that's a good question. Yeah. So yeah, that's a good question. So maybe here I would say no, in the sense that, you know, here I make it like take this instance and make like many copies of that instance. So you take that box here, then you make another box on top, then you make another box on top, and so on. And then now, you know, if I make more than p boxes like this, so here, of course, here I can say, okay, I'm gonna split like only one cluster. So if I put the portal at the very right location here, then I'm gonna be happy. But now if my instance is made of these instances of like, you know, 10 times p copies of that little box here placed on top of the other, then the big red line I'm gonna draw here is gonna be only have p things, and so one of the instances is gonna be bad. So I think you can come up with an instance where even if you don't place the portal, if you cleverly place the portals, you won't have enough portals to be fine with this, to make the error small enough. Okay. Because I think the number of clusters that can overlap, you can make sure that it's like much more than p. So it's not very good. So one thing that we did like back in 2016 with Claire Mathieu and Phil Klein, and this was also like done by Frickstadt, Rezapour, and Salvatpour. Yeah, we had both papers at the same time. Is that we show that local search can actually work there, in the sense that if you take a local search algorithm with neighborhood size 1/epsilon² for the plane and 1/epsilon to the d for dimension d, then you will get a 1+epsilon approximation for k clustering. So this is like almost all clustering algorithms, almost all powers, any power actually that is constant on the objective. So k means, and you can look at the third power and so on. And this also works for planar graphs, low dimensional Euclidean space, and doubling dimension. And the algorithm is very simple. It's like you have your centers somewhere. So here I put it on the grid just to simplify, but your centers can be in the plane anywhere, or like in Euclidean space anywhere. Then you try to move centers. So you try to move 1/epsilon centers at the same time. So here I just depicted one, trying to move one center. You can try to move up to 1/epsilon² centers. You obtain a slightly different solution. You can compute the cost of these centers, like is it a good clustering? Is it better? If yes, you take this solution and you repeat, you start again and you repeat. And if it's not better, then you try to move another set of 1/epsilon centers, and you try all possible set of size 1/epsilon² centers. If none of them improve, you stop. Otherwise, you repeat. And here we managed to show, yeah.
In the previous slide, was the square distance based on Euclidean metric, and would it change if you use other metrics?
Yeah, so square distance is based on the squared L2 norm. Yeah, I think you will have the same issue with L1 norm. Yeah, like if you look at the L1 norm between the vector, yeah, you would have the same issue. I think here it's the same problem.
That goes down, and therefore you'll still be okay.
Sorry.
But in L1 norm, like that would go down, and you might still be okay using the.
No, but the square here that is coming here is because of the k-mean subjective. So the k-mean subjective is the squared of the distance. So no matter you're looking at L1 distance or L2 distance, you are squaring at the end. So
okay,
the issue. Sorry.
Got it. Yeah, understood.
Yeah. Okay. So yeah, exactly. So here we managed to show that you can get like 1+epsilon approximation for k clustering, and the main idea of the analysis is this isoparametric inequality, which tells you that for all these type of metrics, that's the common denominator of all these metrics, like doubling dimension, low dimensional Euclidean space, planar graphs. They have ways of you can use a few points to separate the inside of a ball from the outside of the ball. So for example, if you take a ball of radius 1, you can use, let's say, some few number of points to isolate the inside of the ball of radius 1 from the outside of the ball of radius 1. And when I say isolate, I mean that clients' points that are inside the ball can be served, have their closest center inside the ball. Points that are outside the ball have their center outside the ball. And this is guaranteed because you only need to add a few extra center on the boundary of the ball, so that this property is given. And this is possible only if you have this isoparametric inequality. And there was two issues, of course, out of this work, is that the running time was really bad. It was like, because you needed to try all possible local move. So it was like n to the order 1 over epsilon squared for planar, n to the 1 over epsilon to the d for Euclidean spaces. And it didn't work for facility location, because you can show that local search doesn't work for facility location. Even if you have a tree, for example, if your metric is a tree, you might still get into trouble. So you can't get a polynomial time approximations. Okay. So we bring together like local search and the old approach. And in the follow-up work, we brought together the local search algorithm that we analyzed, and the old approach of this decomposition, quad-tree decomposition, this random decomposition. And what we did is use the quad-tree dissection to find the best local search move. Okay, so instead of trying all possible naive move of 1 over epsilon centers, we can try to use the decomposition of the space to efficiently, using a dynamic program, find which set of 1 over epsilon centers we should replace to get the best possible cost improvement. Okay, it's like a fast local search. And so the key idea we had there is that, so let's consider a solution A that you have right now with your local search. And you want to find the best solution A prime such that A prime is not very different. A prime is only different from 1 over epsilon centers. But A prime is the best local move. It's the best solution you can reach out of A by changing only 1 over epsilon to the D centers. And you want to find A prime. Okay, so first question you can ask is, okay, if I just want to use a constant number of portals, I don't want to use log n portals, I just want to use a constant number of portals, 1 over epsilon to the D, and be happy with it. So when is this okay? So this is okay if the client C is separated from its center F by a line that is not much larger than this, because then the square distance is okay. Like the line L is not much more longer. Like the line L is not much longer than the line that that the distance between the 2 points. So if that's the case, then it's not too bad. We can still use 1 over epsilon portals, and the detour will be proportional to the length of the line. Okay, so that's okay, because the length of the line is smaller than the distance in between, so it's not too bad. The worst case detour is proportional to the cost. And so the issue is that the probability that portals are not good enough for a client C is the probability that the client C is separated from its facility F, or the center F, by a line that is longer than this number. And the probability, so the probability that this happens is the probability that you are separated by a line longer than this, and this probability is less than epsilon. So in this case, we say that C, the client C, is badly cut. It happens with probability epsilon that C is badly cut. For the rest of the time, C is good. We can use number of portals that is constant. So the main algorithm idea that we had in a Soda paper, and then that we use more in the Fox paper afterwards, so for the poor quality, for the badly cut clients, we are going to do something bad. We're going to say, okay, we are going to pay constant time many their cost in opt. So we're going to say, okay, badly cut. If you're a badly cut client, if you happen that you can't use Portal for you, we are going to use a constant factor solution, black box constant factor solution in some sense. But since each client is badly cut with probability epsilon, the total cost increase for dealing with badly cut client using this constant factor change is only order epsilon naught. And the idea is that the remaining client can be dealt with using the standard DP with 1 over epsilon portal. So I don't have time to go too much into the details of this, but essentially we managed to break the analysis into two cases. One case where the client is badly cut with probability epsilon, and in which case we use some sort of constant factor approximation proxy for these guys. And for the remaining client, we can show that we can use only like a constant number of portals. And that allowed us to get, like in the Soda paper, a base local search move. Instead of doing n to the 1 over epsilon, we were doing like 2 to the 1 over epsilon. So that was much faster. The overall running time was like, now for the plane, this is like 2 to the 1 over epsilon to like, some constant. It's not too bad. And then, almost linear time, n times k time log n. And then we had a one-shot approach, and Fox 19 paper, that managed to get us to the running time to be like near linear time, and also to make it work for doubling metrics as well. So slightly more general approach. Okay. And yeah.
Is there any promise that local search works? Because like that you don't get stuck somewhere in a local optima or something.
Yeah, exactly. Yeah. So I didn't have time to present the theorem, but that's the theorem we showed here. That's essentially the local search with neighborhood of sizes produces a solution that is a local optima, that is within 1 plus epsilon approximation for of the optimum solution for all these metrics like minor free, planar graph, constant low dimensional Euclidean space, doubling dimension. So we know here that even though the problem is non-convex or like you can't do much, like that any local optima that you're going to reach with this local search algorithm is maybe not the global optima, but it's not much worse. It's like 1 plus epsilon factor away. So then that's why. But the issue is that the running time was very slow because of this. So then that's what we did all this to speed up the local search, to get something fast for local search. That will bring us to a good local optima as well. And so the issues that we had with local search, we managed to the running time of n to the 1 over epsilon to the d, for example, we now brought it down to near linear time. So that's good. But for example, for planar graph, for minor free graph, this is still the best known for k-median, k-means, and so on. Now the paper is like 5 years old. There is still no progress on getting a faster running time. So we don't know how to speed up local search or even to design a new algorithm that will be faster. And the second issue that I mentioned briefly is that the algorithm did not work. The local search doesn't work. Here is an example where the local optimum is bad. It doesn't work for facility location when you have different opening costs. And so we didn't know how to do it. So we had like two answers. One that we managed to break it, like getting down to near linear time. Now again, for low dimensional Euclidean spaces, we managed to handle different opening costs and to break it down very fast. For planar graph, we managed to solve this question of like different opening costs for a facility location and get n to the 1 over epsilon to some power for planar graph. It's a Fox 19 paper as well, but we don't know how to make it faster for planar. That's still open, like to get faster running time for this. And this is no more using local search, so we don't have local search anymore. Okay, so now let me map a little more this. We can kind of color this map. So there is the region here where you have planar, minor free. I didn't talk too much about bounded high dimension. This is a family of metrics that aims at modeling road networks for which we can show the same level results. Low dimensional, bounded doubling metrics. All this is easy in the sense that we know we can get 1 plus epsilon approximation. So you can't have arbitrary set cover instances and then embed them into these metric spaces and get hardness results. This is not possible. We know, I showed you the proof that, general metric is not easy. It's very much like set cover. So 1 plus 2 over E is the best you can hope for. And there is not much you can do about that. And there's the next question, which is like, if you have something high dimensional, so high dimensional is definitely harder than low dimensional because you have more dimension. So high dimensional is not in the category of easy so far. And general metrics is not, and high dimensional is not as bad as general metrics because the example I gave you with the distance 1, distance 3 for the hardness of set of K-median, it's not clear that I can embed such a thing in high dimensional Euclidean spaces. I didn't give you any embedding. I didn't give you any vectors for the points. So it's not very convincing that you will have such a problem. Okay, so maybe what can we do in high dimensional Euclidean spaces? And that's maybe something we can try to tackle. We can look at whether the distances are given by the L2 distance or by the L1 distance. These are like two different distance measured between vectors, right? So you can look at two of them. You can ask, oh, is L1 metric, high dimensional L1 metric, harder than L2 metric or not? Like, can we prove that L1 is harder than M2? That would be surprising, but maybe. And for the LP metric, let me give you the state of the art. So if you're, so D is the dimension, K is the number of clusters. So let's look at D and K as a parameter. So if D and K is constant and you have in high dimensional Euclidean space, you can get in n to the dk plus 1 the exact solution. And we showed in the Soda 18 paper that this is tight. You can't get better than that. Okay, so fine. So now we can't do exact. So this is for exact solution. Okay, exact is done. We don't know, like it's tight. This is the running time, it's tight. That's it. Now we have to use, we have to go to 1 plus epsilon approximation. So if we want to do 1 plus epsilon approximation, we use a parameter K. So that means that the problem is still hard for K equals 2. So if I am in high dimension and I want 2 clusters, then I can't find the exact solution. So it's going to be hard. So you have to do 1 plus epsilon approximation. And then you can show that you can get linear time, but exponential in K and epsilon, you can get 1 plus epsilon. This has no dependency on D. Maybe it's like ND polylog n, but it's like linear in D. It's only exponential in K and epsilon. And you can get 1 plus epsilon. On the other hand, on the first part of the talk, I told you similar results for if you want to parameterize by D, in the sense that if D is equal to 2, then the problem is NP hard. But now you can have n polylog n running time algorithm that have exponential running time in D and epsilon, and that give you 1 plus epsilon approximation. So 1 plus epsilon, you can do if you parameterize by either D or K. And now the question you can ask is, okay, if I want something that is poly K and D and N, poly everything, then what can I do? And in fact, here comes the interesting results, is that you can get 6.357 approximation for K-means and 2.6 for K-median. And here's the thing that is interesting is that for K-median in general metric, the bound is like 2.67. So we know how to get slightly better than general metric in Euclidean space. We know how to get slightly better. In terms of algorithm, we know how to use a little bit of the Euclidean structure to get slightly better bound. And we have an upcoming paper where we improve these things. So this is going to be down to 2.3 something, and this is going to be down to 5.9 something. So we managed to improve these results to use more and more structure of the Euclidean space to get better and better approximations. So that's good. But what I want to show you right now is how can we try to prove hardness of approximation, because maybe with what I showed you before, you can still hope to get a 1 plus epsilon in poly everything. Maybe exponential in epsilon, but then poly n, k, and so on. So, that's maybe something we can do. And so let me try to show you like some result that we had a couple of years ago on trying to prove hardness of these objectives. And this is cool because I think it's like very geometric. So it's really showing what you can use from the Euclidean structure and so on in high dimension, and try to show hardness results. Okay, so what was known before our works was like 20 years old roughly. So there is the Guo-Kuhler for general metric lower bound that I presented to you, and then there is the L2 metric lower bound that was given afterwards. L2 metric, L1 metric, L infinity metrics. People managed to show hardness of approximation to something that was like 1.0000001 essentially. So you couldn't have 1 plus epsilon for any epsilon, that's for sure, but then you could have like 1.001 approximation perhaps. So this was the state of the art essentially. And what we got in this Fox 19 paper with Karthik was hardness of approximation that was not as strong as we would have hoped for, but that was pretty strong. So we could show like L1 metric up to 1.56, up to 1.14, L2 metric 1.15, 1.06, and L infinity metric. These two bounds are the same as general metrics. So we show that L infinity metric we can get as hard as general metrics. Here I must say that when I mean L infinity metric, I mean L infinity metric with log n dimension. Because if you have n dimension in L infinity metric, you can embed any other metric into L infinity with n dimension. So it's not really telling much. So here when I say L infinity, I mean like really log n dimension. These two are also for like log n dimensions. Okay. So we have a new embedding framework to get, some inapproximability results. Sorry, questions?
Yeah. So in this case, you are saying L2 is kind of the easiest among these three, or like or among all LP now it's going down and then going up from L2, something like that.
Yeah, exactly. Yeah, totally. Yeah, for now it's that's exactly the curve we are seeing when we try to plot it for like different P's. Then you will see like it's L1 is like somewhat hard, then L2, then L infinity, and so and the question that we can ask is like whether it's because of our stupidity, like because we didn't know how to find the right embedding that would also work for L2, or it's because L2 is intrinsically easier than L1, for example, or L infinity. Okay, so that's the question you can ask. Like, is the L2 metric, is the properties of the L2 metric giving you much algorithmic power for solving this clustering problem than the L1 metric? And this, I think, is a fascinating question because you can ask, like, why is L2 easier? Yeah. So I'm going to try to argue why L2 is easier next. But I want to give you the taste of the reduction that we had. So when you want to prove hardness for this geometric problem, the thing you can do is like, okay, step 1, prove hardness in the general metric case. That's what we did. I showed you the general metric case. Then take this general metric instance and embed the reduction, the gadget of the step 1 hardness bound into Rn. And then we are done. We are very happy. The step 3 that comes up usually here is that you realize you can't embed such a gadget without messing up the distances by too much. Because of course, if I take the gadget with distance 1 and 3 that I showed you at the very beginning, but now the distances that are 3 become 1 and the distances that are 1 become 2, then the reduction is messed up. Nothing can be done. Okay, so we have to embed it and preserve the distances. But for this, we need to find, as step 1, we need to find a gadget, a reduction that is embeddable. So the general metric we designed has 2 little structure, like this distance 1 and 3. This is 2 little structure to be embedded. And one thing that is hard here is that for both client side and candidate center side, the degrees of the 1 edges, the distance 1, can be arbitrary. So essentially here, if you have some sort of bicyclic where you have not quite a bi-click maybe, but like high degree here with 1, high degree here with 1, and then a few edges with 3, then we're going to suffer. We don't manage to embed such a gadget. So here, if I wanted to embed this graph where distances are all pairwise 1 across the bi-click, but then distance 2 between these guys, then I won't be able to do it without incurring some distortion in Euclidean space. So we need to kind of have a control on the degrees. So one thing that we are going to try to...
it's like 5:10 now, so maybe we should wrap in around 5.
Okay. Sounds good, sounds good. Yeah. Sounds good. Let me wrap up very quickly. So yeah. So let me try to think about one way to do it. So one thing to do is that we use, instead of the usual set cover, we use vertex coverage, which is you are given a graph and a parameter k, and you want to find k vertices such that you cover as many edges as possible, like a maximum fraction. This is a hard problem as well, but the approximation gap is like 1 versus 0.9292. So it's a pretty small gap. It's not like the 1 versus 1 minus 1 over e. It's like 1 versus 0.9292. And so here we can do the same thing. We can do edge is going to be the client, that's the thing you want to cover, and vertices are the candidate centers. But now the degree of the client is 2 because each edge, so each element of the universe, can be covered by at most 2 vertices, the endpoints. So it can be covered by at most 2 different sets. So now there is a clear embedding that, like, it's a much easier graph to embed. And so from there we will manage to show that under unique game conjecture, the problem is hard. And essentially, so I don't have time to give you the embedding, but you can actually get the embedding. So maybe it's like a good thing you want to think about it, but each candidate center corresponds to a vertex. So vertex VI of the graph going to be embedded at location 0 everywhere except at the highest coordinate where it's 1. And edge VI VJ is going to be 0 everywhere except for where it's 1 and 1. For the i's coordinate and the j's coordinate. These are 2 extremities. And then you can show that for an edge VI VJ, if the candidate center that is VI or the candidate center that is VJ is in your solution, then the distance is 1, and otherwise it's going to be 3. So then we have again the 1, 3 thing here that we have embedded. But and we can decide that, you know, vertex coverage 1 implies the k-means cost is epsilon. Otherwise, it's like, you know, you can cover a 0.9292 fraction for which you pay 1 versus 1 minus 0.9292 for which you pay 3, and that gives you a gap of 1.15. So this is good, but the gap is bad. And so what we did in like further work was to introduce a new hypothesis, because that requires like some combinatorial, extremal combinatorial theory results that we don't know how to prove right now, and that have been open for like 100 years. So it's not that it's like, you know, but assuming that this conjecture that is 100 years old is true, then this conjecture is going to be likely to be true as well. And then assuming this conjecture, we could show this following striking result, that this is where I'm going to conclude, that in the L1 metric, the hardness for these two problems is as hard as the general metrics. And for the L2 metric, it's slightly weaker. And this suggests that L1, so L1 is as hard as general metric space. The question is like, this conjecture, is it true or not? This is upcoming soda paper, and yeah, we are still working on it. It's not clear. It's probably a hard question, so we have to think more. But that helps us characterize complete the picture here that says that, oh, L1 is high dimensional, L1 is hard, but L2 is okay. I mean, L2 is presumably okay. Maybe it's just that we didn't manage to prove the height hardness. But I intuitively believe that L2 should admit better algorithm than general metrics. Okay, so I have a summary of open problem, and I'll stop here. So for the first part of the talk on planar and minor free metric, there is open question of like finding efficient approximation scheme for k-median or k-means in planar graph, minor free. Efficient approximation scheme for non-uniform facility location, even in planar graphs. P-task for non-uniform facilitation in minor three, this is still open as well. I'm getting a P-task there. And for high-dimensional Euclidean space, there is this conjecture of Johnson coverage that we introduced in this upcoming SODA paper, showing that L1 is L2. L1, and there is a separation between L1 and L2. And I think this is a pretty cool open question. And here is my favorite open problem, where, so I'll spend 1 minute on that, which is facility allocation. In general metric, we know upper bound of 1.48 approximation for general metrics. We know hardness lower bound of 1.46. So we can think of these two as being like tight. Okay, upper bound, lower bound for general metrics are matching almost. The hardness we have for L2 under our new results is below 1.2. So can we show that for high-dimensional L2, we can get better than 1.46 approximation? And that would show that L2 is easier than L1. That will be a concrete example where L2 is easier than L1 for facility location, for a clustering problem. Okay. And I believe that this is true. It's just a question of finding the right way of proving it. And then there are like other problems, like even if you want the one median problem under L2, we don't know exactly how to find the one median problem. It's a hard problem, like to compute it exactly. It's a convex problem, but the right approximation you can get because the coordinates are maybe not expressible as rational. So you have to do some approximation. And it's not clear exactly what the right complexity of the one median problem, which is the complexity class of the problem. And this is the second one is like a very cool problem. Like I give you n strings, and under edit distance, you want to find the one median. So you want to find the string that is not necessarily in n input string, like an arbitrary string that is minimizing the sum of the distances to your n input strings. But 2approx is easy, and we don't know how to do better. And I'm going to stop here and thank you for your attention.
Okay, yeah, let's thank our speaker. If you have any other questions, I think this is a good time to ask.
I have a couple of questions. So first question is about the portals. So normally portals is a useful idea in many other problems like TSP, Aurora's p-task algorithm also use portals. Yeah. So now your new algorithms, does it have implications for TSP for different like metric spaces or something, or?
I mean, well, I mean it's similar, but it will not give you directly something for TSP. I think it's like there is some algorithmic idea there that are specific for clustering that I wouldn't know how to use for TSP, for example, to get better bounds.
And the second question I had was regarding the local search. So in some problems like 3-dimensional matching, people showed that you can use log n, like instead of 1 by, you can use log color coding, etc. So those kind of tricks, are they possible here as well? That instead of using constant number of local search, you use log n number of local search and still it is solvable.
Yeah, that would be nice. Yeah, this I don't know. I know. Yeah, there's Mark Sagan, for example, has this paper. There is also a paper by Silvio Latenzi and Christian Soller who showed that you can still get a constant factor using local search if at every step you sample according to the k-means plus distribution which center you want to swap. So for example, like to explore the neighborhood, you just use the k-means distribution to sample here the k-means plus distribution. So it's good. It's giving you constant factor approximation. I think the constant they managed to show is like 1,000 or something. So they managed to say it's 1,000 approximation, for example. So it's not clear how you would do that for like 1 plus epsilon, for example.
Yeah. Thanks. These two are my questions. And again, thank you very much for accepting our.
Sure. Yeah.
Hi, Vincent. Question that's probably quite basic. I was wondering, this keeps coming up, but how come? Why is k-means harder than k-median? Like, is there any intuitive way of understanding that?
I see. Yeah. So why is k-means harder than k-median? Yeah. So in terms of approximation, yeah, it's because you know, when I was giving this example of distance 1 versus distance 3, then essentially then we were getting like you know, the guys that are not covered, they are going to pay 3. Now if you are looking at square distances, these guys are going to be paying 9. So now you immediately get a gap, a boost in the gap of the harness, in the harness, just because like instead of paying, like, you know, if I could put a 9 instead of a 3 for k-median, it's not the metric anymore, but I would get the same harness than k-means essentially. But it's just that k-means is more costly, and that's why you can see higher hardness of approximation. But it's not like there is nothing harder intrinsically from that. It's just that whenever you make a mistake, you square the mistakes, so it's much expensive.
So it has so the question is like so the follow-up question is whether it has something to do with the technique, or is there intrinsically something in k-means that makes it?
No, I think it's intrinsically k-means that is this. It's like whenever you because you square the distance, whenever you make the mistake, you square the mistake. So that's it. Yeah.
Are there any other questions?
Hi, so can you expand on the conjecture you mentioned, the JCH conjecture?
Yeah. So, okay. So the JCH conjecture that I mentioned is essentially saying that, okay, maybe I should just present it. That's going to be slightly easier. Yeah, so the conjecture is essentially, you can see it as a generalization of vertex cover. It's a slightly twisted generalization. So you have a universe E. These were the edges in the vertex cover. Now the edges E are T tuples. And the question you are asking is like whether they are like K T-1 tuples, such that for all my T tuples that I have, this is my input. My T tuples are my input, and I have a K. There exists one of the K T-1 tuples that is contained fully in my tuple, right? So for each of my T tuple, I want that there exists one of my centers here, one of my K centers, which is a T-1 tuple, that is fully contained in my tuple, T tuple. And in fact, the optimization question you can ask here is like, I want to find a set of K T-1 tuples that maximizes the fraction of T tuples that satisfy this property, that are contained, that fully contain my K T-1 tuples. And from there, you can define a natural embedding. Like essentially, you can generalize the embedding that I was describing here, where you put like one coordinate and so on. You can, so if this problem is indeed hard, if it's hard to distinguish between this version, like the case where everyone is going to be, for each tuple, you contain 1, versus there is only an alpha fraction that is satisfying this. If this is a hard problem, then you have a natural embedding in the Euclidean space, such that will give you a result for k-median and k-means, and it's a generalization of the vertex covered result. And if you can show that this problem is hard with alpha here being like 1 minus 1 over E, then you will get immediately the result that I showed you for k-median and k-means. If you can show it to be like 0.8 instead of 1 minus 1 over E, then you will still get something.
Okay, thanks. And thanks for the nice talk.
Sure. Thank you.
Okay, let's thank the speaker again and stop the recording.
Sure. Thanks everyone for